Hello everyone, welcome to this fifth lecture in the NPTEL course on Riemannian geometry. So last time we started our review of smooth manifolds, so we will continue with that today. Last time I think I reminded you of the definition of what a smooth manifold is, and then how we choose coordinates etc. on a smooth manifold. What does it mean for a map to be smooth and so on. So the aim of today's lecture will be to talk about tangent spaces and tangent bundle, right. So like always, n will denote a n dimensional smooth manifold Okay, so here is a definition. Let P be some point in M. A germ at P is an equivalence class of pairs U comma F, where U is some open subset of M and F is a smooth function on U, right. So when do we say UF is equivalent to another pair V comma G? If and only if there exists an open subset of U intersected with V which contains the point P. So there is an open neighborhood of P which is contained inside both U and V, such that the restriction of F to W is identically equal to the restriction of G to W. So that means locally near P both F and G actually represent the same function. Away from P they might have different values, you do not care, but at least near P they will have the same values. So then we call this pair equivalent. So then we denote by C infinity P to be the set of germs at P. Okay, and basically our notation, so in our notation we will usually forget this open set and we will just denote a germ as the equivalence class of some function at P. Okay. So this will be our notation. Okay, a remark is that this space is a real vector space, okay, with the usual addition and multiplication of functions, with the usual addition and scalar multiplication of functions. Okay. So now a derivation at P is an R linear map. So it's sometimes denoted by D. So this is an R linear map on the set of germs. So in other words, it's a linear functional on the set of germs, which also satisfies the following Leibniz rule. That if you take the product of two functions and take their germ and apply D to this, this is simply going to be f of P times the derivation applied to G plus G of P times the derivation applied to F, right. So this is essentially the familiar product rule from that we learn about in calculus. Okay. So then the the tangent space to M at this point P is defined simply by the set of derivations. Okay. And the key fact that we need, which is not obvious from the definition, so this requires a proof, and I am sure if you have taken a course in smooth manifolds you must have seen the proof, so I am not going to repeat the proof, is that this tangent space is an n dimensional vector space over R. Okay. So in fact one can also write down a basis for this vector space. So in fact if x1 up to xn are local coordinates on some open set containing this point P, then one can actually write the tangent space as the span of these basis vectors. Okay, so what is del by del xi, where suppose phi from u to Rn is the coordinate map, and let us say u1 up to un are the standard Cartesian coordinates on Rn, then del by del xi at P. So it is a derivation, so it should act on a germ and spit out a real number. So it acts on this germ of this function. Well, f being a germ, it represents a smooth function in a neighborhood of P. So what you do is you simply compose this with phi inverse. So f composed with phi inverse will now be a smooth function defined in some neighborhood in Rn, and you calculate its usual ith derivative and plug in phi of P. Okay, so this is the definition of these basis tangent vectors. All right. So I will also use the following notation or shorthand notation: del I will represent del by del xi, this partial derivative operator, and del I at P will be this basis element. So by definition this is just you compose with, so if you have a function f, you compose with phi inverse and take the partial derivative with respect to the ith Cartesian coordinate, right. So this will be my notation. Okay, so now for any vector space, if you have a basis, you might choose a different basis to work with. So then it is important to understand what is the sort of change of basis, right. So here given a coordinate system, I have defined a basis for my vector space. So obviously if I change the coordinate system, I would get another basis, and it is important to understand what is the change of basis matrix, right. So in linear algebra, if you have a vector space, if you choose two bases, then to go back and forth between the two bases you have a linear transformation or a matrix, right. So similarly here we can compute what the change of basis looks like. So if y1 up to yn is another set of coordinates, okay, near this point P, so then maybe so I'll let this del by del x be this row vector given by the basis vectors in the x coordinate system. Similarly, I have a row vector of basis vectors in the y coordinate system. Okay, and I want to understand what is the change of basis to go from the y basis to the x basis. So the formula is quite simple and elegant. The row vector consisting of the y basis is simply given by multiplying the row vector consisting of the x basis with what is called as the Jacobian matrix. Okay, so this is the Jacobian matrix evaluated at P. So this is the so-called Jacobian matrix. Okay, what is the Jacobian matrix? So if you look at the ijth component of this matrix, that will be the ith component in the x coordinate system, the derivative with respect to the jth component in the y coordinate system. Okay, so so you can think of these xi's, the coordinates xi's, as functions of the new coordinates yi's, and then once you think of them like that, you can also differentiate in terms of the y coordinates, and that gives you precisely the Jacobian matrix. Okay, one thing to note is that if you reverse the order, if you take the Jacobian matrix of y, the derivatives of y with respect to x, then that is the same as this inverse. Okay. All right, so this is as far as the change of basis goes. So now we set Tm to be the union, the disjoint union over of the tangent spaces over all points in M. Right, so so essentially you have your manifold. So maybe let me draw a picture in R3. So let's say we have a surface. At some point here you have a tangent space. At some point here you have another tangent space. At some point here you have yet another tangent space, and so on. So now we want to look at the whole collection of all possible tangent spaces. Okay. So that's called that's denoted by Tm, and this is called the tangent bundle. Okay. So right now, I mean, just taking the disjoint union, this is just like some other set, right? But it turns out this is this is more of a structure. So again, this is something you must have seen in a smooth manifolds course, that Tm can be given the structure of a manifold and moreover the natural projection map. So there is a natural projection map where you project the Tm, the entire tangent space at P down to the point P. So the natural projection map makes this into a vector bundle. Okay, so if you haven't seen what a vector bundle is, don't worry about that. We won't actually use this anytime, but in case you're curious, I think maybe you can just go and look this up on the internet if you haven't seen this before. But in any case, we won't be using the notion of a vector bundle at all in this course, but I thought it's worth mentioning that the tangent bundle is not only a manifold, but it has this additional structure of being a vector bundle. So loosely speaking, a vector bundle is basically over a manifold is a smoothly varying family of vector spaces, okay, of the same dimension. So that's essentially what it means, but it's fine if you haven't seen this notion before. So there's another notion of a tangent bundle or a tangent space that's much more sort of geometric, and we'll keep referring to that. So this idea of defining the tangent space as derivations, the motivation comes from the observation that that Rn can essentially be identified with the directional derivatives at a point, right? So the analytic way of defining the tangent space is via these derivations. They're essentially calculating directional derivatives of your function, of any given function at a point, right? On the other hand, geometrically, if you are given a surface in R3, so a more sort of geometric definition. So if you are given, let's say, a surface in R3 and a point, how would you think of the tangent space at this point, right? How would you think of the tangent vectors to your surface at this point? One sort of easy way is that you look at curves, you look at curves lying on the surface and then compute the velocity vectors of those curves, and then look at the subspace of in this case R3 spanned by all those velocity vectors, right? So that's a much more geometric way of thinking of tangent spaces. So that actually gives you an alternate definition of the tangent space. So one can also define the tangent space to be the set of equivalence classes of curves, okay, where gamma is a curve on M. At 0 you get P. So this is a set of curves passing through P, but you also have to define an equivalence relation. So we define, let's say, gamma 1 to be equivalent to gamma 2 if and only if there exists a coordinate chart containing the point P, okay, such that there exists a coordinate chart centered, let's do centered at the point P, such that if you take the composition phi composed with gamma 1 and phi composed with gamma 2, both of these are now curves in some open neighborhood in Rn, curves passing through the origin. Why the origin? Because each of these curves takes 0 to P, and P by this coordinate chart is sent to the point 0. So now you can just take the derivative at t equals 0. So if these two curves have the same derivative at t equals 0, we declare them to be equivalent, and the set of all such equivalence classes of curves. So that's basically formalizing this notion that a tangent space is nothing but a collection of velocity vectors of curves, right? So that's a much, as I said, much more geometric way of thinking of tangent spaces. Okay. So finally, for today's lecture, I want to talk a bit about vector fields. Okay, so here's a definition. So a vector field on M is basically a map. So vector fields are usually denoted by capital X, capital Y, and so on. So this is a map that takes a point on the manifold to the tangent bundle such that, firstly, if you compose it with the natural projection map, you get identity. This is equivalent to the statement that X takes P to a tangent vector in the tangent space at P. Okay, these two statements are obviously equivalent. And secondly, I want X to be smooth. Okay, so I have already said that the tangent bundle is actually a manifold, right? But I didn't explain what the manifold structure is. So let me at least explain what it means for a vector field to be smooth. So i.e., for any coordinates, so you take some set of coordinates on M, then because the tangent space at every point is spanned by these basis vectors, so let's say these are coordinates on some open set U, on some open set U in M, then if we write this vector field X restricted to U as so let me write it this way. At every point you can write this as a linear combination of the basis vector so then for every point P you get this collection of components of your vector in this particular basis, right? So then smoothness basically means that we need each of these xi's to represent smooth functions on this coordinate neighborhood U. Okay, so that is what we mean when we say that a vector field is smooth. Okay, so this is the definition of a vector field. We will denote by this fancy X of M to be the set of all vector fields on M. Okay. So one thing to note is that chi of M is a C infinity of M module. So again, it's not important what if you don't know the general meaning of being a module is, but for us what this the important properties are the following. So sorry, CM module and R vector space. Okay, so it has the following properties. If you are given X and Y here and A and B are real numbers, then you can define a vector field given by Ax plus By. Okay. Secondly, again, if you have xy here, and now let's say you have smooth functions on M, then you can also define multiplication by smooth functions. Okay, that will give you another vector field. Okay, so in that sense, it's a module over the space of smooth functions. So another point to note is that X defines a derivation. So we already saw a definition for what a derivation on the set of germs means, but in fact X defines a derivation on the space of smooth functions. So what do I mean by that? So that means X will give me a map from C infinity M to C infinity M such that it's R linear whenever A is in R and F is in C infinity, and being a derivation means that it satisfies the following Leibniz rule, that if you multiply two functions and apply X, then that's going to be just this. Okay. All right. Finally, I should also note that that there is this notion of a Lie bracket so this takes in two vector fields and spits out another vector field. Okay. So the definition is that x comma y is xy minus yx. So when you think of vector fields, you should think of derivations or first order derivatives of your function, right? A vector field defines a way of taking first order directional derivative, right? So the nomenclature here is that xf is called the derivative of f in the x with respect to this vector field x. So in the direction of x. Okay. So vector fields represent first order directional derivatives of functions, but here you seem to be taking two derivatives, right? You're first applying y, then applying x, and similarly here. But it turns out that when you subtract these two quantities, you actually end up with a first order derivative. So this indeed, it's an exercise which again, if you haven't seen this, it's a good exercise to work out that this actually defines a vector field on your manifold. Okay. Alright, and finally I want to talk about the derivative of a smooth map. So one can use the notion of tangent spaces to define derivatives of smooth maps. So let's say f from M to N is smooth. Then for all P in M, we define the derivative of f at P to be a map from the tangent space of M at P to the tangent space of n at f of p. And what is this map? So it takes a tangent vector. A tangent vector is a derivation on a germ. So df applied to x will be a derivation on the germs at f of p. So this acts on a germ at f of p. And what is the answer? The answer is just you apply x to the derivation of g composed with f at p. So this guy is now going to lie in the set of germs at p, so you can take the derivative in the direction of x. Okay. So this is the definition of the derivative map. So actually in terms of this other alternate definition in terms of equivalence classes of curves, it's even easier to write down the derivative map. So if you take an equivalence class of a curve at p, the derivative map basically just sends it to an equivalence. If you look at f composed with gamma, that will now give a curve passing through f of p in n. So you just take the germ of you just take the equivalence class of that curve. Okay. So that is basically the derivative map in terms of curves. Okay. So for many things working with the definition of tangent space in terms of curves is actually very convenient. Like for instance, here the definition was much simpler. On the other hand, when you are doing calculations, it's actually more useful to work with the derivation definition of tangent spaces, right. So it's always in math, it's good to have sort of different viewpoints to view the same notion, so that in the given problem at hand one can use whatever notion is more convenient. Alright, so let me finish this lecture by discussing one of the most, if not the most important theorem in differential calculus, namely chain rule. The chain rule actually takes a very simple form in terms of this derivative map. So the setting is, suppose you have a map f from m to n and a map g from n to some other manifold L, then you look at the composition. So that's just going to be g composed with f. Then the chain rule says that the derivative of g composed with f at some point p in m is just going to be the composition of the derivative of g at f of p composed with the derivative of f at p. Okay, so the derivative of compositions is a composition of derivatives. That's basically the chain rule in all its glory, right? Okay, so yeah, maybe I'll also draw this. So at the level of the tangent spaces, you basically have this map. So this is dfp, this is dg f of p, and then this is going to be the derivative of the composition. Alright, so that's so far as tangent spaces and vector fields go. In the next lecture I will review the cotangent space. I'll remind you what one forms are, and then I'll also remind you of what tensor fields are. Okay, tensor fields and differential K forms are. So that's going to be the content of the next lecture. Alright, so that's it for today. That's it for this lecture. I'll see you in the next lecture, and thanks for your attention.